Good morning from day one of lockdown. Today what we're going to be doing is finding out the chemistry behind how batteries work. Just sorting myself out. I have to let you know I do have a 7-year-old called Alfie in the room who's currently waving at me. He's currently playing Roblox, so if he runs into shot... In fact, come and introduce... Come over here, Alfie. Come here, there you go. So this is Alfie, my little boy. He occasionally makes the odd noise. He's playing Roblox at the moment, but but he will be doing some schoolwork a little bit later. But if he does run into a shot, oh, he did his schoolwork yesterday very fast. So what we're going to be doing is talking about the chemistry of how batteries work. So what we'll do, we'll go onto the PowerPoint and we'll work our way through that. So the chemistry of how batteries work is all to do with electrode potentials. And I personally think that actually this area of chemistry is so important for the future. If you think about it, we have all of these sources of renewable energy, so wind, solar, and things like that. Sorry, just adjusting my microphone. Wind, solar, etc. And the big challenge is that actually it's only sunny for half the day, if it's sunny in this country. It's only sometimes windy, most of the time whenever I'm going out or anything. But the thing is, we need to capture that energy. If you recharge your mobile phones, you'll find that actually they get quite hot. And the reason for that is that the energy that you put in to recharging your mobile phone is expressed as heat. Batteries, modern batteries we have are only about 30% efficient, which means that only 30% goes into recharging the cells, and the other 70% is expressed in other ways. So, for example, heat coming out. So it shows it's a very wasteful process. So one of the big energy challenges at the moment is to make better batteries. And as always, I think that the batteries that are going to be made in the future are going to be more efficient. They're going to function better. They'll be able to take more charge. They'll be able to recharge more quickly. But again, these are challenges that within 4 or 5 years, you guys are going to be taking up, because by the time you leave university in about 4 or 5 years, these are the sort of jobs that are going to be available for you. Power storage. Another alternative idea of power storage is using large capacity capacitors. But again, there are challenges with that. If you want to learn about capacitors, probably better to talk about physics. I apologise if there's a slight creaking at the moment. What that is, that's my headset, whenever I talk, moving and making a bit of a noise, but it's better than the fan noise, which is coming out of my computer with that microphone. So, we're going to be learning about electrode potentials. And electrode potentials are what they say on the tin. It is the amount of voltage that an electrode gives out. It's the potential difference of an electrode. We're going to define some half cells. We're going to talk about metals in contact with metal ions, and we're going to see how we can get the voltage from other systems which aren't so easy. We're going to talk about half cells. So this is basically one electrode in with one metal, for example, in a solution of its ions, and we'll talk about how we construct full cells and work out voltage and things like that. We'll also find out how these relates to our redox potentials and the redox equations. It essentially finishes the story that we have. So, first thing, keywords, standard electrode potential. Now, this is the amount of energy in volts that you get from a half cell compared to something called the standard hydrogen half cell. We'll talk about what that is, and it's all at the correct... I'm sorry, we've just got an Alfie walking over. And it's all at your standard conditions. Of course, for those of you who do physics, EMF stands for electromotive force, so it's essentially the potential that you get generated. So it's called a voltage to those of us who aren't physicists and electronic engineers and things. So what is a half cell? So if you have any redox equation, for example, our copper 2 becoming copper by gaining 2 electrons, that would be the equation. Whoa, there we are, it's all working. That would be the equation for a half cell. How would we make that? Well, actually, we can get copper metal. We can get some copper 2 ions in the form of something like copper sulfate, and we can put them together and work out and get the voltage from those. If you look at this, if I have copper just sat in copper ions, there is an equilibrium set up. So the convention is that actually we have our electrons on the left-hand side of this, always on the left-hand side, and when we're writing our redox equations, always have the electrons on the left-hand side. What we'll see later is there are rules as to which one is reversed, and this actually explains things like displacement reactions and things like that. So, half cells. These half cells are the working components of our battery or our investigation when we're doing a redox equation. So if I have a metal in contact with its ions, so here I've got some copper metal, I have a solution of copper ions, so for example copper sulfate or copper nitrate, all at 1 mole or 1 mole per decimeter cubed. We have this standard sort of copper half cell, and if I measured this against a standard, and the standard is the standard hydrogen electrode, which we'll talk about shortly, I would find that I would get a voltage of plus 0.34 volts. So not a particularly useful battery, but we can measure the energy of this process by getting this cell potential if we measure it against a standard hydrogen electrode. So if I have something like this, this would be zinc, for example. So we can see we've got zinc electrode here, and we have a solution of zinc ions. Now, what do we know about the reactivity of zinc compared to the reactivity of copper? I would hope, if you remember back to sort of year 7, year 8, year 9, when we do displacement reactions or when we put acid on these things, we'll see that actually zinc does react more vigorously than copper if you put something like hydrochloric acid on there. Never do it with nitric acid because that can end up bad. But we can see that actually zinc has a potential of minus 0.76 volts. So we can see that actually we get the reverse voltage, so it's going from zinc to zinc 2. It wants to become zinc 2, and we can see that actually we have a greater voltage. So it's worth saying, if you have a metal and a solution of ions, this is your most simple type of half cell. So what about things like gases? Because we can see actually if we have some gases, for example chlorine or hydrogen, these also react in redox equations. We can do redox reactions with them. So in order to quantify them, we have a special type of electrode. So if we don't have any solid in our system, we use an inert electrode. So that is our inert electrode. This is usually made from platinum, and these platinum electrodes are actually quite expensive, which means we don't actually, we can never really sort of find many of them. I did find some in the drawer the other week, and I think hopefully most groups have shown our standard hydrogen electrodes. So what I do is I put gas into here at 1 atmosphere, and I put it in a solution of 1 molar H plus ions, so 1 molar acid. If we think about it, if it's something like sulfuric acid is a dibasic acid, which means that it lets off 2 H plus ions for each molecule that's in there. So that means that we would only need 0.5 molar H2SO4 for this to happen. So if we do this, and we do this with the gas at 100 kilopascals or 1 atmosphere, we have a cell potential of 0. And because of this cell potential being 0, and I do apologise for my terrible work with this graphics tablet, I am just getting used to it. Because we've got this cell potential being 0, that means that actually this standard hydrogen electrode is a good standard to put against everything else. So we set our standard at 0 volts using this standard hydrogen electrode, and this is what we do to work out the voltages of any other redox systems. So again, this is called a standard hydrogen half cell or a standard hydrogen electrode. What if I was going to look at something like a more reactive gas? So I've got hydrogen in this first one. If I wanted to look at the chlorine chloride system, I would have exactly the same setup. I would put chlorine gas into here at 1 atmosphere. I would have some Cl minus ions, so I could use something like NaCl or I could use HCl, as long as it gives us a 1 molar solution of chloride ions. The electrode again has to be platinum, and I think this shows you why it has to be platinum. Platinum is very, very unreactive, and which is why it's used to make jewellery and catalysts and things like that. Most metals would certainly react with chlorine, and I know definitely gold would react with chlorine. Not very quickly, but actually you can make a nice solution of gold chloride. So this is why we use platinum, because it is very, very chemically inert. If we do this, we would find that we get a voltage of plus 1.36 volts. And in fact, as I said to you, in order to measure this plus 1.36 volts, we would make a circuit with this standard hydrogen electrode with this one, and we'd compare them against each other, and we should find at standard conditions that we have a potential of plus 1.36 volts. So what about solutions of 2 ions? So for example, we have iron 3 and iron 2, quite an important one. We could have a platinum electrode, and let's have a look at the size of this thing. This is going to be a very expensive electrode. And what we'll do is we'll have standard solutions of Fe3 and Fe2. We would have to sort of put them together so that their molarity or their concentration would be relative 1 molar with 1 molar. And we could find, using this system, that you'd get a potential of 0.77 volts from the system. If I had solutions of oxidizing agents, so for example this nice purple one represents potassium permanganate. If I have MnO4 minus turning into Mn2 plus, and we've been looking at this quite recently, we just put the 1 molar solution of this in there. We use a platinum electrode again because it's not going to react with the oxidizing agent, and we put the solutions in, and it should give a potential of plus 1.52 volts. If we look at this, it actually shows that with this high voltage, why we have permanganate as a good oxidizing agent. It wants to oxidize things. So looking at it, all of these things have in common the fact that everything's 1 molar. The experiments would ideally be done in standard conditions, so your 298 Kelvin and 1 mole per decimeter cubed solutions. So if I put 2 electrodes together, I should make a cell potential, or a comparison of the cell potentials. But in order to do that, I have to have standard conditions, and they are 298 Kelvin, 1 atmosphere, and different solution, and 1 molar solution concentrations. Of course, if I vary those, we will change the cell concentrations and the voltage that's given off. And next lesson we'll be talking about how we predict and how we know what's going to happen when we change the solutions or any of the conditions. But it's really important you understand that all of these voltages are only ever done or only ever given out when you have the standard conditions. So this is our standard hydrogen electrode, and it's really important that you remember what this looks like, because they do ask questions about it quite often. So we have a glass tube with a platinum electrode dangling down there. We have an inlet for the gas which goes in at 1 atmosphere, and we have a 1 molar solution of H plus ions. So that is how we operate our standard hydrogen electrode. You'll see here that this wire, whoa, I didn't know, what is that? I've never had that happen before. This here is just the connection that you would use to connect the hydrogen electrode or the platinum electrode into your circuits. As I said, remember the standard hydrogen electrode has electrode potential of 0 volts. So this is an example of an electrochemical cell. So we have our standard hydrogen electrode over here, and we have a redox system over here. And you can see what I'm doing is measuring the voltage of that system. You can see it's being measured against the standard hydrogen electrode, which has a voltage of 0 volts. You'll also notice this thing here that I haven't mentioned before. This is the salt bridge, and this completes the circuit. We can see here that actually if I just measure the volt of this against this, we wouldn't have a complete circuit. There would be no exchange of ions, so therefore we would not get any voltage from it. So we need to put this salt bridge in to complete the circuit. Typically what you make the salt bridge from is a solution of something like potassium nitrate or potassium chloride, something where the ions are very, very mobile and are able to move around freely, conducting electricity. We usually use a saturated solution to make sure that there are plenty of ions around. So if we had these two electrodes sat there together, what we would find is that we would be either turning zinc 2 into zinc with hydrogen becoming hydrogen ions, or we'd have zinc becoming and hydrogen ions becoming zinc 2 and hydrogen molecules. I've mentioned what the salt bridge does, but just to remind you, it is to allow the circuit to be completed, and it allows that electrons and ions can actually flow, and it causes the system to conduct electricity. So let's have a look at the Fe3 Fe2 plus system. We can see that we have a platinum electrode here. We have 1 molar Fe3 plus, Fe2 plus. We have our standard hydrogen electrode over here. Stand by, I'm just getting a call. I will come back to this in a moment.